Welcome, welcome.
Hello, everybody coming in.
I can't tell if people are quiet or if Zoom is dead.
Yeah, so we're trying something new this month, everyone, and we're actually giving you the chance to let us see your lovely faces. So if you're comfortable, feel free to just give us a hello and maybe say where you're tuning in from. If that's in Edmonton, maybe say the name of your neighborhood, and we can get a good sense of who's going to be joining us.
Hey, Warren. My name's Steve Pearson. I am indeed here in Edmonton. I'm in Strathcona, and I work for a company called Beano AI.
Awesome. Welcome. Good to see you again.
Good to see you.
Strathcona, great neighborhood. All right, my name is Warren. I'm tuning in from Queen Mary Park. I'll be your host tonight. We're going to give people a bit more time to jump in, seeing as we're still about 5 minutes away from start time. So if anyone else is tuning in and wants to say hello, then please feel free.
Hello everyone, this is Ali Reza. I live in Calgary. I'm a master's student in UAlberta and also work for Metrics.
Awesome. Welcome. That's great. It's awesome to have our neighbors to the south. I think that's one of my favorite things about these virtual events is we get so many people from across the country. The past couple events we've had people from as far as Nairobi and Tokyo. So that's pretty cool. Calgary, we're excited to have just down the road.
I'll introduce myself. Hi, everyone. My name is Vonimir. I'm currently have my video off because I am trying to make sure that my internet runs as smoothly as possible for this meetup. So you can't see my face, unfortunately, today, but welcome.
Thanks, Vaughn. What neighborhood are you joining from today?
I'm joining from Oliver, Edmonton. Well, I guess it's being rebranded now, so I'm not sure where I'm tuning in from.
My name is Matt. I'm calling in from Cloverdale, and unfortunately, you have to see my face today.
Thanks, Matt. This is great. Looks like the people are trickling in here, so that's fantastic.
I guess I didn't realize that there was rebranding happening. Is it Oliver Square is passé?
I'm gonna flip that over to Swan.
Yeah. So there's a new initiative that the Oliver Community League is working on, and that is renaming this neighborhood that is currently named the Oliver neighborhood. And I don't know too many details other than the headlines that I read, but maybe somebody else does.
Yeah, I'm in the same boat as Vaughn on that one. I don't have the facts, but I think there's good reason for the change. Regardless, it is a great part of the city to live in.
Yeah, Dave Mueller, I'm calling in as well, and I'm calling in from Belgravia. And I think what I was hearing on the news regarding Oliver is the person that it was named after actually didn't a lot of their actions in the city, they were a prior city councillor, and some of the actions and things that they stood for were, you know, no longer socially acceptable. And the Oliver School, there was an initiative by the school as well there. And then by the Community League, I think started that initiative first to rebrand to somebody who better reflects, you know, the character of the people in the neighborhood and the values that we stand for now.
That's great. Thanks for sharing. All right. Anyone else want to say hello as we hit the 5 o'clock mark here? We'll be starting in just a few minutes. We'll give some folks time to jump in and join us. I have this infinite scroll thing happening as I try to go through our attendees right now and see everyone's smiling faces.
Hi, Warren. So I'll introduce myself. So I'm Stephen Kaiser. I'm Director of Member and Market Insights at Service Credit Union, and I've been to a number of Amii events. And I was lucky enough last year to attend the Deep Learning Summer School, which was a really interesting opportunity. I'm also actually involved in the DAMA Edmonton chapter. I'm on the board. I'm the president. And I'd also want to let everybody know that we're starting up again right away. We've got a webinar coming up this September 30th, and we're going to be doing lots of webinars throughout the year. So I hope a lot of people that are attending this particular get together can attend as well. So thank you.
Awesome. Thanks, Stephen. All right, well, we've got time for another couple of folks. If you want to say hello, feel free. We've been asking everyone who's joined in, if they're interested, they can keep their camera on and just unmute themselves and give us a little hello and where they're tuning in from. To make it a little more interesting for all of the folks that are tuning in from Edmonton, we've asked that you just let us know what your neighborhood is.
So I'm David Snowball. I'm undergrad student at the U of A, and I coming in from Belgravia right now. No webcam though. Sad.
Strong. Belgravia is a great place to live as a student. Love that neighborhood. All right, it's good to have some undergrads in the house. That's fantastic. It's a good mix of people today. All right. Well,
my name is Diana Peterson. I'm in a startup company in Calgary in the data science area.
Fantastic. Well, welcome, Diana. I believe you're not the only one tuning in from Calgary tonight as well, which is fantastic. We're always happy to connect with our neighbors to the south. All right. Well, we're just a few minutes after 5 here, so I'm going to take a moment again to say hello and welcome. We've got a pretty fun lineup tonight, and I'm actually really excited at experimenting with this format a little bit. So we've been collecting feedback from everyone attending these virtual meetups. We're still very early on in running virtual AI meetups. So it's been fun to get some suggestions and feedback and be able to basically build events that are better for you. So one of the changes that we made tonight is rather than the typical webinar format, we're able to set up a Zoom meeting and really kind of get the most out of having all these great people that are here attending the meetup to be able to participate a little bit more and have that back and forth. So there will be a learning curve. It might be a little bit sticky at times, but we're going to roll with it. So that's something I'm looking forward to. All right, we've got Jolene from Garneau as well. That's fantastic. We're big Jolene fans here at Amii, so thanks for coming tonight. Okay, so for those that may not know or are attending for the first time, Amii is the Alberta Machine Intelligence Institute. We have a deep history of decades of world-leading AI research and training that's been happening at the University of Alberta. That's really put us in a great position as thought leaders globally. whether you're a student, a business, or just looking to get more involved in the AI community, we have a whole host of great programs and resources to support you as you do that. You can reach out to us through amii.ca, the new amii.ca. We recently launched a new website, so please check it out. We really love it. And you're welcome to drop us a line at hello@amii.ca as well. For those joining the meetup for the first time, I'm going to run through a few housekeeping items before we jump into the meat and the good part of tonight's event. But we try to keep these relatively brief so that you can dive in and get the most out of your Thursday evening. Again, we're not running the webinar format. We're doing this as a meeting. So the goal there is to have it be a little bit more interactive. We'll have two presenters do short presentations, and there will be 10 minutes at the end for Q&A. So you're welcome to hold your questions for the end, but you're also welcome to use the raise hand feature, and we're going to leave it to the discretion of the presenters to decide if they want to take that question or if they want to save it till the end, whatever they think is going to work best. And again, bear with us. If things don't go perfectly, that's totally intentional. Again, we want to leave a low bar so that we can keep doing better and better every time. I will also note that this session is going to be recorded, and we'll be posting these talks later on Amii's YouTube channel. So again, if you feel inclined, please raise your hand and ask a question, or use the time that at the end after the presentation. We'll have a chance to chat there as well. In lieu of the usual hanging out and schmoozing and carrying on that tends to take place after these types of events when we host them in the Mercer warehouse, we're encouraging everyone to take the rest of the evening and check out the Startup TNT Discord. So there's a happy hour that takes place on Thursday evenings. It's really been well adopted by the tech community and is a great place to meet with companies and investors and students and researchers. So please feel free to jump right in. I'll be sharing that link in the chat. They run this every Thursday night, and they'll even send you a free kombucha or craft beer to participate. So it's something I'd encourage you to check out down the road. Normally I say please give a nod of approval, and knowing that we can't see everyone, but in this case, please join me with a silent clap or a thumbs up or something like that, a big smile, to welcome our first presenter of the evening, who's going to be talking about explainable AI, Mohammad. So I'll hand it over to you, Mohammad, and we can jump right in. Thank you so much.
Thank you, Warren. Let me share my screen first. And okay. I'm Mohammad. I'm a master's student at U of A, and I'm also a researcher at Amii's XAI lab. And I also live in Garneau in Edmonton, close to university. So I want to talk about XAI, and first I will briefly introduce why we need XAI in this presentation today. Then I will have some brief definitions about explainable AI, which are somehow required for the next steps, which are LIME. That's a very famous framework that many people use and rely on for explainable AI. And finally, I will introduce BARBE, Black Box Association Rule-Based Explanations, which is our extension to LIME, and that will conclude this presentation. So first, I want to start with why we need XAI. Because I'm interested in airports and airplanes, I thought maybe I can give you an example of airplanes and airports and how AI was used in that domain in 1980s. So there was this expert system called GATES, which was an airline gate assignment and tracking expert system that was used in John F. Kennedy Airport in New York City in 1980s. So the goal of this expert system was to assign airport gates to inbound and outbound flights. And I'm not going to go into the details of this system, but it was a sort of a constraint satisfaction expert system. And it had two levels: the initial daily plan, which was given by airlines, And then it also had the real-time plan, which was according to flight delays and weather changes, and that was very usual in 1980s. So you may wonder what this has to do with XAI. So the answer is that even this system in 1980s, it was providing some sort of explanation to its users, the operators in the airport. So for example, it could tell them why gate 2 was not assigned some flight, or why this flight was not assigned to some gates. And I have picked these two figures from the paper describing this method. And as you can see, it was explaining that, for example, gate 2 was not assigned to flight 803D because the plane can't use that gate. Probably that was a 747, that gate couldn't accommodate that one. So how about the current AI systems? So these days, we have some AI systems that are working greatly. For example, we have machine translation that can translate a sentence from a source language to the target language pretty well. And we also have deepfake that I think everyone has heard about. And these, compared to what, for example, Gates could do in 1980s, they are in a whole different level. And they are AI-based, they are pretty good, and they can outperform humans in some aspects. But while it may not be very important how machine translations translates one sentence from a source language, say Farsi to English, everyone is interested to know, for example, why that AI system is telling us that this patient has cancer. So actually that explanation part that Gates was providing in 1980s, that is something that unfortunately many systems have not made any advancements in recent years. So for example, as I said, we have AI saying that that patient has cancer, and most deep learning methods cannot explain why. Or if, for example, we have a customer who is denied a credit, and then AI cannot explain why, that is not acceptable to users or customers these days. So these two examples are somehow very clear and obvious, and everyone agrees that we are not gonna use such systems because we cannot trust them. But I wanna go beyond these trivial examples and give you an example where it seems very obvious that, yeah, let's trust that system. It's not a critical, like, life or death thing, or it's not about a customer denied a credit or a loan, say. So this is a real example. Amazon had a hiring software that was used to recommend whether they should interview an applicant or not, but it turned out it was biased against female applicants. And eventually, because of this issue, they had to stop using this software, and also the team that was developing the product was disbanded. And of course, now everyone says that, yeah, Amazon was hiring only male applicants. But if they had used some sort of explainable system that they could understand how it was making the decisions, for example, which features it was looking at, that software, they could have easily avoided this problem. And probably right now that software was in production and not somehow left somewhere and not used anymore. So beside that, there are some domains that explainability is very common, and everyone agrees that we somehow need that sort of explanation, as I said earlier. So medical or precision medicine, legal domain that, for bail decisions. Also, autonomous driving is an important domain that, for example, if you want to investigate to find out what caused an accident, you should know that, for example, what was the decisions made by that autonomous driving, whether it's autopilot or any other autonomous driving system. And finally, I think everyone has heard about GDPR, the General Data Protection Regulation, that is from European Union, and it was enacted in May 2018, and all companies must provide an explanation for their automated decisions that have a legal or a significant effect on users. So GDPR is not just about explanations, it covers different aspects, but one of the aspects which is somehow new is about providing this explanation. In fact, explanation or providing reasons isn't something very new. I can show you that in just this case of denial of a credit, there was an act in 1974 from US that all companies must provide reasons, for example, that why a person was denied a credit. And it's a similar thing, but it's not just about the credits, it's in general that and applies in any automated decision that is made by companies. So if you have European customers, whether your company is located in Canada or not, this already affects you, and I'm sure that you are familiar with this one. But what about Canada? Is there any similar pattern in Canada, any similar law in Canada or not? So the answer is somehow yes. There is this new directive on automated decision-making systems, but it only applies to federal government departments that requires them to comply with this directive as of April 1st, 2020. And they must provide an explanation for decisions according to the impact that decision has. So they should first use a tool called algorithmic impact assessment tool to determine the level of impact their decisions has on the users. And then based on that level, they should provide the proper explanation to the individuals that are affected. So what's this AIA or algorithmic impact assessment? It's a questionnaire actually that eventually will give you one of these 4 levels that I have put here. And as you can expect, the level 1 decisions are systems that are the ones that their decisions has little to no impact on the users, on their health, rights, economic interests, and other stuff, and the impact is usually reversible. But for example, a level 4 system is a system that the rights are affected significantly, and such decisions usually are irreversible. And it's not just about users or individuals, but also entities or communities. So the corresponding explanation varies to some degree between these different levels. For a level 1 system, you only need to provide some sort of explanation in the form of frequently asked questions, and that is only for common decisions. But for a level 4 system, you must provide some meaningful explanation, and that is unique to that decision that you have made to that individual or entity. So this is actually only for federal government departments. But I think based on what we saw with GDPR, in the near future, in the next couple of years, a similar law will be enacted and will require all companies, all private companies, to also provide some sort of explanations or some reasons corresponding their automated decisions to the people that are affected. Because again, there are so many private companies that make decisions that have very critical impacts on the citizens or different entities. So now I want to provide you with some definitions in XAI that are somehow needed for the next part of the presentation. But this will be short. I want to distinguish first between interpretable and explainable system. So normally in a machine learning task, I can use this one. So we have the training data or some sort of experience, and through a learning process, we usually have a learned model. And then when we have a new observation, we predict or infer the class label of that new observation or some sort of action. Interpretation means we can look at this learned model and understand what is going on inside it. So it's about the user inspecting and understanding its composable parts. And this is some sort of static feature. It's not about individual instances or new observations. It's just about the model itself. And a simple example would be a linear model or a decision tree that the user can check that decision tree and, for example, check the values, the parameters inside different nodes in the decision tree. And everyone somehow can understand to some degree that what is going on inside that decision tree. So this is interpretation, and these models are usually called interpretable models. But there's a spectrum of that, if you have a decision tree that the depth is, say, 100, then that's not that much interpretable anymore. But that's something that you can still understand to some degree. So it's a spectrum. And we also have explainable system. An explainable system is a system that can provide explanations to the user. So this is not about user inspecting the system, but the system providing some explanations or some insights about how it came to that conclusion. So this is about the reason, providing reasons why a decision was made at inference time. But these decisions may not help us understand the internals of the system. So as I showed you earlier, Gates was telling us why, for example, that plane couldn't fit that gate. But we still don't know how Gates works, right? This is just about some insight or some explanation about, for example, why that decision was made, but we still don't know how it got to that conclusion. So now I want to provide different categories for XAI methods. We have different types of explanation techniques. One of them is concurrently constructed explanations that they usually build the explanation along with the inference. So that means that you create both of them simultaneously. For example, you can think of a text prediction, a sentiment analysis task that the goal is, for example, to understand whether this movie review is positive or negative. And the model is built in a way that initially it picks a few of the words in the sentence or the document that is our input. And then using those words, it predicts the final class as a positive or negative. So in this case, those words that the system has looked at could be our explanation, because we want to know what features, for example, the system was using, right? And those features were really the features that were used by the model. The post-hoc method, however, relies on, doesn't create that explanation at the same time as the inference or prediction, but it does so after the prediction. And it has two subcategories, model dependent and model independent. A model dependent one is a method that relies on the internals of the system. So for example, in a deep learning case, it has access to the internals of the system. It knows the weights and any other parameter that is inside the system, has access to the architecture, and you can use that information in order to provide the explanation to the user. A model independent one, however, doesn't have that access anymore. It sees the model as a fully black box one. So it's just somehow the input and output, and it doesn't know what's going on inside that black box model. So in this section, I want to discuss about LIME. It's local interpretable model agnostic explanation. And model agnostic is another term that people use for model independent ones. So essentially in LIME, it tries to explain any black box model, regardless of how it is built and how it makes predictions. So the goal is explain each decision of that black box model, each new observation. So in LIME, LIME provides a sort of importance score for top K features of the data point that you have given to it. And K, this number is the user specified parameter. So you ask that give me top 10 features, and LIME will usually exactly 10, sometimes less than 10 returns that many important features and their corresponding scores. And it also works on tabular data, text, and images. So I want to explain you how LIME works in just one slide. The idea behind LIME is to build a neighborhood around the original data point. So this is the data point that the user is interested and wants an explanation. So essentially what LIME does is that it creates similar data points using perturbation techniques. And then we have these new data points and then queries them using black box model and obtains their corresponding labels. So it says, okay, these ones are blue, these ones are red. And then it trains a linear model, a linear regression in this case, using this synthetic data set. And this synthetic data set and somehow is that neighborhood that I just mentioned. And this linear model is used in order to create the explanation. So in fact, the coefficients of that linear model is used to provide the final explanation to the user. As you can see here, this is an example from LIME, and it is on the mushroom dataset. So the goal is to classify each mushroom as either edible or poisonous. And given these features, LIME has determined that, for example, odor has 0.26 importance, gill size has 0.13, and so on and so forth. So this is actually the explanation that LIME provides. And as you can see, what I can observe here, these are actually coefficients of the linear model, linear regression. But what I can observe here is that, okay, probably this one is more important than this one, and this one is more important than this one, and so on and so forth. So these numbers, although they are based on linear regression, so if we change the value of this one, it will change. Maybe the class label, maybe not, we don't know. So, but these numbers are not that helpful to us. In fact, there are multiple shortcomings for LIME, and that's just one of them. In addition, we have the accuracy of the explanation is not that great always, so that is different, but this is to some degree understandable because model-independent methods do not have access to the internals of the system. And that's a very challenging part because model-dependent methods have access to the internals. You know what's going on inside your model. And because of that, it's understandable that the accuracy is not that great always. And the other thing is that unlike what they claimed in the beginning that they can explain any black box model, they need some probability score from black box model. And without that, they cannot train that linear regression model. I mentioned earlier that explanation is not very useful. Those numbers are not meaningful. And finally, what's the best K? So this is, as I said, a user specified parameter, but the user obviously doesn't know how many features are important, right? And you just are gonna set it very randomly, 10, 20, you don't know, right? And because of that, you may have to try different numbers and see, for example, which features exist and among all these different explanations and eventually come up with your own best method, best explanation. So now I want to introduce BARBE. It's called Black Box Association Rule-Based Explanations. So it uses association rules, sort of a rule-based classifier in order to provide explanations. So what are the improvements that it has over LIME? First, it can provide alternative forms of explanations. It not only can provide that important features that I showed you earlier LIME could, but it also provides some rules. And this is very important because rules, first, you can understand them better. That, for example, feature 1 and feature 2 implies this class label. It's not those numbers anymore. In fact, the authors of LIME later came up with another paper, Anchors, that creates one rule instead of these numbers and provide the explanation in form of one single rule. But BARBE can also show the associations among these different features. So if you say feature 1 and feature 2 in a rule, which I will show you later, that means these two features have some sort of association between each other. And finally, another thing is that it provides multiple rules. That means if you have feature 1 and 2 in one rule and feature 3 and 4 in another, this means these are multiple causes that led to that decision by the by that black box model. And here you are providing or getting different causes, which, for example, Lime, it couldn't provide that information. There is no association between these features or correlation, in other words. And also, there are no multiple causes. These are some just numbers. So this is the architecture of BARBE. It is to some degree similar to Lime, but there are some big differences in some sort of transparent model that we use. It's called SIG-Direct, but we made multiple changes inside this classifier. And so the big idea here is that, the main idea here is that given this data point, the user says why it is classified red. And then in the first step, BARBE creates the neighborhood around that. So these are perturbations of the original data point. So different features are modified in order to create this one. And there are most of these data points are very close to this one. So it's a normal distribution that is based on the proximity of these data points. Then, using our black box model, we label all of these data points to understand, for example, what is going on in this space or in this neighborhood. And here, we then use an interpretable model. In our case, it's associative classifier. It's one type of rule-based classifiers in order to create the rules. And once we have these rules, and by getting the original data point, we get the proper and relevant rules. And using these rules, we extract the important features from them. So these two together, these rules, and also these important features will be the final output or the explanations that is provided by BARBE. In fact, we call them alternative forms of explanation. These are two different ways that the user can either use the rules if they want, or they can use some sort of important features. So this is an instance of class dataset that I have run through BARBE, and here is the output. So on the left side, for each row here, I have these three separate rules that explain that, for example, what was the association between different features present in that instance. And here is the important features that, for example, you can see feature 6 is more important than feature 3, and 3 is more important than feature 4 and 7. So there are numbers here, but these are not that helpful, that insightful, and the order is the most important thing that everyone should rely on. That's something that I think it's worth mentioning. And another thing maybe is needed to better understand this information is that here for continuous features, we have to discretize them and create these buckets. So here, these numbers are the bucket numbers. That feature 3, for example, is in bucket 1, feature 4 is in bucket 3. It's the same information here, but that is used actually here in all of these rules. So there is no time actually to go into the detail, but these are called applied rules in, if I want to use the technical term, in rule-based classifiers. So that is the sort of the rules that we use in order to provide explanation. So how did we evaluate our method? That's a very tough question because it's very difficult to compare and see, is your explanation correct or not? And it's very difficult whether your model is model dependent or model independent. However, If you have a model independent method like BARBE or LIME, you can take advantage of an interpretable model instead of your black box model. So instead of having a real black box model, you can use a decision tree. The model doesn't have that access to the internals of the system. It provides its own explanation, but because this model is interpretable, we can extract the real cause or the real explanation from our decision tree. So for a decision tree, for example, what is the real explanation? What features were used by black box model or by decision tree in order to predict the class label of this new instance? They are features that were used in the path leading to that leaf that corresponds to that data point. So we extracted that information from decision tree and compared it against the explanation that was returned by BARBE, LIME, and also Anchor. That, as I said, it tries to provide one rule using a high precision method. Another thing that we compared was the order of important features that we used a measure from information retrieval called RBO in order to compare how the orders looks like. And I ran experiments on 11 different data sets, and I have provided the F0.5 score and RBO here. So I use F0.5 here because, as I said, precision is more important, and we wanted to have a highly precise explanations. And because of that, during tuning, which has different sections that I didn't have time to go into details of that, we intentionally tuned BARBE to provide high precision. So we don't need that K anymore. That's one big issue that LIME had. And also Anchor provides high precision. So it provides very few features, but on the other hand, these features are highly accurate. And that was also our intention, that we don't say a feature is important, but if we say it is important, you can rely on that and with a very good high confidence. And RBO compares the orders between features. So if a feature was the most important feature based on the ground truth, and if LIME or BARBE or any other method also ranked it first, it should be assigned a higher score compared to putting that in the end of the list. And yeah, that is it. And thank you. I would be happy to answer your questions.
Awesome. Thank you so much, Mohammed. I'm just back at the chat, a couple questions that came in. So the question here was, are all interpretable models explainable? That was from Payam.
Somehow yes, because so when you know what is going on inside your interpretable model, like a decision tree or a linear regression or logistic regression, you can also explain somehow how it made that inference. So that path inside the decision tree or the non-zero features in a logistic or linear regression models, that are the features that were used in order to make a prediction. So yes, all interpretable models are also explainable.
May I ask a follow-up question to that?
Sure.
It's Payam here. Yes, I was a little bit sorry if this is a simple question, but so you use the word cause in a few places casually. So if you're saying that linear regression models that are interpretable are also fully explainable, I wonder if, so by explainability here, we're just meaning correlation between some set of features. Is that how you're defining it? Because to maybe naively, I would expect some kind of cause and effect to be part of the explanation.
That's right. The problem is that current machine learning models cannot provide causes. They just can understand the correlations in the data, right? So, and that's all that explainable AI can provide you. So if I have some sort of mushroom dataset or any other dataset, I cannot provide that real causes as, for example, humans normally can do, because somehow we are causal systems, right? But machine learning models, they just can understand the correlations among different features.
Okay, fair enough. Thank you.
Awesome. We had another question come in from, I believe it was Scott. So he said, when you speak of the user understanding, is that a layperson or someone involved in the creation of the model?
That's a very good question. Let me say it in this way, that ideally, any explanation provided by a system must also take into account who is the explainee. That's the technical term we use. That if you want to explain something to a student, you would explain it in one way. If you as a human being want to explain some math equation to a student, you would explain it in one way. But if you want to explain it to a math professor, you would explain it differently, right? And ideally, any explanation framework must be aware of their audience, must be aware of the explainee and their knowledge. But current systems, they just usually provide explanation in the forms of input. And that is, for example, a heat map for an image, or as I showed you, some features in the input. These are the very first steps, and there's way to go for that ideal sort of explanation.
Thanks. That's a great answer. I feel like it's relevant for your right now versus your.
Yeah, we wrote a paper, actually. We have discussed that in detail. I had mentioned that a couple of times. And so if anyone is interested, they can, of course, read that paper, and I would be happy to be contacted if they have any question.
Awesome. So we've got time for maybe one or two more. One thing that we have the ability, if you're interested, you're very welcome to unmute yourself and fire away with questions here. Also welcome to put them in the chat if that's if you're more comfortable there as well. All right, Matt, question from you.
Yeah, I had a question. What happens if you have correlated features? So let's say I am judging a mushroom based on its color and its height in centimeters, and I have another feature that its height is in inches. Isn't that could that mess things up?
So yes, technically, before training any model, you should get rid of those correlated features, right? And what, for example, Lime does is that they use ridge regression in order to avoid this collinearity issue. And association rule-based classifiers can somehow take care of that, and that usually doesn't happen here.
Awesome, thank you. Okay, last chance for questions. Going once.
I just had a question where I can find that paper. I came in a little bit late, so I was just hoping to catch up if I could.
Here it is. Okay.
Maybe you could drop that in the chat
yes,
after you stop presenting.
That's right.
Yeah, that sounds great. All right. Well,
Okay.
Please join me in thanking Mohammad for sharing this presentation with us tonight, and wishing him all the best with his defense coming up in what, a couple of weeks?
Next week.
Next week. All right. Awesome. Well, all the best. Looking forward to it.
Thank you.
Thank you. And before we jump into our second presentation tonight, we'll have a few moments in between. I have some exciting news to share with you all, and then I'm going to create a bit of a chance for some of you, if you want to take a quick 10 seconds and say what you're working on, And if you have an ask or some sort of call to put out to our very talented community with us tonight, whether you're looking for some to fill a position you're hiring for, or if you're just looking to promote a new app that you've launched and are looking for users, or anything like that, just want to make sure you have a chance to make that known and become a familiar face and someone that people might be able to reach out. So feel free to share a contact email, anything like that as well. And so in the good news department, something that I'm very excited about, you may have seen the announcement recently from the provincial government, the Ministry of Environments and Parks. So we're thrilled at Amii to be launching a new program focused on emissions reduction. So you can learn more about this at amii.ca. If you click on Industry Solutions, you'll see this new program called REMI, R-E-M-I, Reducing Emissions Through Machine Intelligence. Our first cohort will launch this fall, and we look forward to working with some of the best energy companies on how to adopt AI for greenhouse gas reduction. I think this is a really exciting opportunity where we have this intersection of world-class AI here in Alberta, and combining that with our very, very well-known energy industry. There's going to be some really exciting work done through this program. And you can apply if you're part of an energy company. You can go directly to amii.ca and up to participate. We'll be launching more cohorts down the road as well, with focuses in areas outside of energy as well. So excited to have that out there, and you'll be hearing more about that soon. But for now, I'm going to pass it over to Stephen, who can give us a quick plug about Vino AI.
Thanks, Warren. Yeah, hi, my name's Steve Pearson, and I work for a startup called Vino AI. We're still in the development stage, but we're developing a mobile sommelier app that will take users through a traditional wine tasting. So you can select a wine and we'll help you taste it, tell you what to look for in the wine, and then gather your sensory preference data on that wine and turn that into recommendations and a personalized wine club. So you'll be able to sign up for 6 bottles a month or 12 bottles a month or whatever it is, and we'll personalize that wine club to your individual tastes.
Awesome, thanks, Stephen. That sounds excited to hear what wine pairs best with an AI meetup, and we can maybe we can pull that out for next time.
Yeah, for sure.
Fantastic. I'll leave a quick chance. Just unmute yourself if you'd like to jump on and share a quick 30 seconds. Now is the time.
I wouldn't mind. So I'm a physics student doing machine learning research at the Tom Baker, but I'm also a director for NeuroNexus. It's kind of like a 6-week hackathon challenge design program where we take real challenges submitted by industry and researchers and pair them with teams of like multidisciplinary teams of like computer science or medicine or business to try and create like an MVP. So there's a lot of interesting crossover between machine learning and neuroscience. A lot of neat challenges coming in this year, and the winning teams get over a portion of over 50K in awards. So anyone who wants to apply or submit a challenge, feel free to contact me, and I'll put our website in the bottom. So that's about it.
Awesome, thanks so much. All right, last chance, going once, going twice. All right, well, that's fantastic. I'm really glad we're able to leverage this this forum to share some of the opportunities that are out there. It's always exciting to hear. I'm is that the interesting things that beyond. So thanks for taking the time to share what you're up to. And now we're going to jump right into talk number 2 here. So please provide a warm welcome to Matt Taylor. Over to you, Matt.
And now I'm unmuted. Awesome. So my talk is going to be a little less technical. In this setup, I cannot see the Zoom chat, but I would encourage people to either raise their hand, I can see that, or just unmute yourself and jump in. That is totally fine. So what I'm talking about today is reinforcement learning. And specifically, what is it and why you should care? And even if you know what reinforcement learning is, hopefully you will learn something new during this talk anyway. So I'm Matt. I've been doing reinforcement learning, RL, since 2003. And I came to Edmonton just a few years ago from the US, in large part because of the awesome people that are at the University of Alberta. I've worked in both companies and university. Right now, I'm 4 days a week at U of A, and I'm 1 day a week at Amii. So I get the best of both worlds. I get to do fundamental research that can change the world, maybe eventually, hopefully. And I can also do stuff here and now on companies. So my two foci are real world RL, which we'll get to, and also thinking about how humans can interact with these RL agents. So with that, you've probably all heard this before. There are multiple flavors of reinforcement learning, of machine learning. And machine learning is a statistical, data-driven approach. It gained popularity in the 80s. And now everyone loves deep neural networks. Deep neural networks are not the same as machine learning. They are just a tool you can use for it. Similarly, there are parts of AI that are absolutely useful that are not machine learning. So things like search and logic, there are still many types of AI that are useful that are not strictly machine learning. There also is, I've seen this a few different times, that data is the new oil and AI is the new electricity. And I kind of like those analogies, especially in Alberta. And thinking about, look, we've got this technology. It is changing things. It is changing the world. If you ignore it, if you don't know about it, you will get left behind. So that's one of the motivations that I think people need to learn about reinforcement learning. So there are these kind of three flavors of machine learning. The most common is supervised learning. So thinking about, let's take a stock and some features on that stock, and is it going to go up and down, up or down? Or maybe I predict how much that stock is going to go up or down. Then there's the unsupervised, look at a bunch of stuff. Is there fraud? Is there not fraud? What's sticking out? And then there's RL, and it's really a different kind of beast. So in reinforcement learning, we've got this agent, which is interacting with the world. So over time, this agent is taking an action, getting a state and a reward, and it's trying to maximize the reward over time. So in supervised learning, you get an input, you make a guess, and then you're told the right answer. In reinforcement learning, you're never told the right answer. So it can be more difficult. So in reinforcement learning, let's think about, I'm in this environment taking steps over time. And I'll give you some both toy and real world examples in just a few slides. But let's think maybe the game of chess. So I'm in a board configuration and I move my knight, and then the other person moves. And no one comes down and tells me, no, moving the knight was the wrong thing. You should have moved the rook. Instead, I just get this reward feedback at the end of the game. So it's very sparse. I just get it at the end, and it's time delayed. So from this, you won or you lost, you can figure out over time how to interact with the environment and eventually beat your opponent. But this environment is going to be either a simulator or you can be acting directly in the real world. But if it's not a simulator, then it might cost you. So a common example of reinforcement learning is robotics. So if I have a robot that's learning to walk, as that robot is interacting with the world, it's wearing down. Its actuators are breaking down, the gears are getting messed up, the battery charge is getting lower, and eventually you have to replace it. Oh, also, you have to pay the graduate student's salary who's sitting there replacing the battery all the time and picking it up when it falls down. So really, you want to think about learning in a data efficient way. Another example, let's say you're learning to trade stocks. When you are learning to trade stocks in the real world, when you're not acting well, you're losing real money. You've got a big incentive to learn quickly. Another difference with reinforcement learning, one of the key things you think about initially is the difference between exploring and exploiting. So you could say, let's take another example where I am learning to figure out a good path to drive to work. And you normally take this one road and it seems pretty good, but maybe you want to try a side road. Maybe that would be better. Maybe you want to try a side road when it's snowing. Maybe you want to avoid that hill when it's snowing. So thinking about, do I want to do what I think is best right now, or do I want to try something new because maybe it's better? And the real tricky part is what happens if the environment is changing. So I'm driving to work, I've got my best route, and now all of a sudden they're repaving the road. So now the environment has changed and I probably need to explore and try something else. But in this setup, we can think of this agent's interacting with the environment, and there's at least three things the agent could be trying to do. The first could be automation, right? You've got Bob. Bob has been doing his job for the past 30 years, which involves shuffling folders around, and you realize, well, if we just put this into Excel, we could automate this. But you could also think of, I've got a program that can do this for me, and I had some very smart people spend years writing this program. But it's possible that reinforcement learning could do a better job. And we've seen that in the research field, we've seen that numbers of times, where a reinforcement learning agent has found novel solutions or just better solutions. And finally, there's the completely novel process. It could be that by interacting with the environment in this sequential decision process, you are able to do something new that your company could not do before. And that's where I think one of the most exciting applications of where reinforcement learning lies, is trying to find those real innovations, which of course is much harder to identify than saying, well, let's just speed up this existing process. There are so many good examples of supervised and unsupervised machine learning in the real world, where companies are making lots of money using it all over the place. And it's disappointing RL is not more widely adopted. Reinforcement learning has been making lots of gains recently. For instance, in Dota, in StarCraft, in Go, outperforming world champions. But if you go to a business and say, hey, look, I got this method that can play video games, unless they're a video game company, they're probably not going to care a whole lot. So reinforcement learning has slowly been building up more use cases. So things like in finance, in healthcare, things like education. And there are all these other places that reinforcement learning can be used. The 2 points I would like to try to hammer home in this brief talk is that my hypothesis is that reinforcement learning is a mature technology that is ready to get out of games and ready into the hands of companies that aren't FANG companies, that don't have billion-dollar research budgets. And if you can take the time to just learn a little bit about what reinforcement learning is and where it might apply, then if you can identify one of those situations, then you know when it's time to pull in a reinforcement learning expert, or when it's time to bug Amii, or send me an email and say, hey, does this make sense? And if it does, then you could make that investment into figuring out this technology, because it is a different framework. It's a different setting than standard machine learning, supervised learning. So I can think about RL having a few different goals, but in general, it's trying to maximize this real valued reward. So I could think about going back to the stock trading performance. Maybe I really care about that initial performance. Maybe I want to make sure I don't lose all my money and go bankrupt. Or maybe I'm talking about minimizing my time. And, you know, if I get to work a little bit slower the first few weeks, it doesn't matter as long as I find the best way to get to work. So there's some kind of personalized trade-off there. But you could think about minimizing the final performance, how fast you learn. You could be reducing human effort. So if I want to solve a new task, I could either sit down and spend months programming it, or maybe I can come up with an RL solution that can just do that for me. And like I mentioned before, you may be able to discover solutions that you had not thought of, and you may be able to handle non-stationary environments. If I'm sending a robot up to Mars and one of the wheels gets jammed, reinforcement learning has the chance of saying, okay, it's not working the way we thought it would. Let's explore and try to learn some more and see if we can still do something. So let me walk you through a toy domain. So we've got Wally here, and he's going to wander around this grid world, and he wants to get that +1. Good robot. He wants to avoid the -1. So we can reason about this by saying, well, I've got some number of states. I actually can't reach this state because it's just a wall. I can't go outside of these 12 squares. I can only move in 4 directions. Can't move through the walls. And to make things slightly interesting, there's a small chance I'll slip to the side. So if I try to go up, there is some chance I will end up going to the right. There is also a small step penalty. So every time the agent takes an action, it gets a little negative reward, encourages it to get to the goal faster. The goal of reinforcement learning is to learn a policy. How am I going to act? In this state, what action should I take? So we looking at that, this is obvious, right? We're just going to go up and around, bang, done. Well, it's a little bit more complex. So here's one example. So here, yes, I do go up and to the right, but remember, I also need to think about what I do in every state. So I need to think about, oh, I'm going to go down around the bottom. Maybe if I'm up, if I'm at this point right next to the -1, I'm going to go up. And this has a moderate penalty at every step. Now, suppose the penalty is smaller. Is anyone willing to unmute and explain what the heck is going on in this state that I'm circling? Take a guess.
Is it banking on sliding sideways?
Yes, exactly. Because in the upper right, you say, I'm going to go up, but there's a small chance you would get to the -1. Down here, there's such a low step cost that you're just going to bump into the wall and eventually you get to one side or the other. So you will not get to that -1. In contrast, if you get a large step cost over here in the lower right, dude, life is too hard. It's not worth it, man. Just give up right now. The agent's better off just ending the episode, getting that -1 instead of getting the pain at -2 every step. So choosing this reward can be a little bit tricky. You can have different behaviors with just slight differences in the reward. So that can be one thing you need to think about if you're going to use reinforcement learning. Okay. Super important, real world domain. Hopefully you have all seen this game before. So, Flappy Bird. This bird is, at this point, very bad. This poor bird is using reinforcement learning. Reinforcement learning often behaves randomly at the beginning. This bird is not getting past any of those pipes. Oh, it did one. It got lucky. well, okay, this is getting boring. Let me fast forward to an hour of training. Hey, the bird learned something. Okay, now let me fast forward to 2.5 hours of training. I don't know how many of you have played Flappy Bird. It was a few years ago, but I could normally get past about five of these pipes. So this is a superhuman bird as far as I am concerned. I'm not the best Flappy Bird player. But we could think of this as a reinforcement learning problem. So the transition function, before we were talking about how Wall-E moved in the world, here, this game that was on Android and iPhone is going to control how the bird moves. Any guesses of what the action is? Does anyone remember playing this game? Warren's doing it. I see smiles.
Hey, you'd tap the screen to make the bird fly up. Yeah.
Thank you. Now we're allowed to keep going. And then there's the reward, which can be just how many pipes I've passed. I want to maximize the number of pipes I passed. Now, it turns out you can play optimally in this game if you know 2 numbers. And those 2 numbers can completely summarize your state. Any guesses what 2 numbers the bird needs to know in order to act optimally?
Is it height and speed?
Height, I agree with. Speed, I don't, because in this particular game, the bird is always going at the same speed. But
oh, right.
Height is good. What's the other one?
The length of the press, maybe? That changes the height?
Nope. So, and in this, again, it's a game-specific thing, sorry. When you press, you get 1 flap, and longer presses don't get you anywhere.
Is it the gap between the bars? Like how big the gap is?
Very close. Unfortunately.
How about the gap between taps? Like how fast?
How fast you tap it? The distance to what?
To the pipe.
Okay, so I've got the distance to the pipe and the height to the bottom of the next pipe.
Yeah.
So I think you could do something with tap frequency, but I think that would be a little bit trickier. And it turns out all the pipes have equal separation. So this is the perfect example of, if you have played this game, this is not too hard to figure out. If you have not, and you're just getting this random guy in an orange shirt telling you about it, it's a little bit hard to come up with a good state representation. But with some domain knowledge, you can. So that's what this person did. Random guy on the internet who had this nice demo, and he's got some simple code online if you'd like to see it. So let's take this a little bit further. We had some Amii fellows developed the ALE, the Atari Learning Environment. So going back even further than Flappy Bird, all of these different Atari games, agents could learn to play them. And you could go and think about hand-coded state representation. So like in Pong, thinking about how far is the ball from me, above me, and so how far is the X and Y positions from me. So I could come up and hand code all of those things. Or in 2015, we get the deep learning breakthrough in reinforcement learning, where deep learning could play directly from pixels. So this was a game changer. Instead of having a human expert come in and decide what the agent needed to know, this was an example where deep learning could learn what to pay attention to. So if you know stuff about the domain, you should absolutely use it. If you don't know enough about the domain, you might be okay if you can use the right technology. The final example I'll give is a cool example from DeepMind, where they improved cooling at a server farm improved the bill by about 40%. So all of this equipment is interacting with other equipment and the environment. The system's got to adapt to different changes in demand and load, or changes in the weather, and every data center is unique. So you can't just come up with one way of doing this. So perfect, reinforcement learning problem. I define the state. I have my engineering friends pick out what are the things I need to look at. I can think about what machines I want to power up or power down or slow down. The reward they chose is looking at how much energy was used for actual compute versus energy used for cooling. And then again, the transition function is the real world. So here's an example where they were not learning in a video game, not learning in a simulator. They were working on the real stuff, which means if these actions were not well defined, there could have been bad things happening. So maybe if the actions are poorly defined, maybe you would lose quality of service guarantees. Maybe you would cause harm to the machines. So hopefully they take that into account and made this safe. So those were just 3 examples of where reinforcement learning could be used. Yes, I am.
Sorry to interrupt you. I guess before you move on, I was wondering if there is a link to the previous talk that Mohammed gave. I wonder, like, given that, let's say for Flappy Bird, you have that very compressed, sparse state representation that would be perfect. But let's say you didn't know that, you trained your RL algorithm and you figure out an optimum policy. Is there a way to extract that representation afterwards?
Yeah, so the
idea explainable RL maybe?
So the idea of representation learning is really interesting. So thinking about if I have the wrong features or I have too many features, and trying to figure out how to construct them or choose them. But you're right. Also, if I have this, let's say I use a deep neural network, and now I hand it to someone and say, will you use my product? You may need to make it explainable. And there are ways to try to make it explainable, which I think I'll touch on in just a few slides.
Okay.
Great. Well, while we're stopped here, does anyone else want to yell? Either jump in right now or put up the hand in the participants list.
A quick question.
Please.
My name's Diana. How would this apply with perhaps quantum computing? The way that you specify weighting and rewards seems how it can also be set up for quantum computing formulas. Has that been explored?
Not by me. I do know that quantum is being used for machine learning, and machine learning is being used for quantum. I don't know specifically about reinforcement learning, but if there is that kind of sequential decision process where you're making different choices over time, there's a chance RL could be useful.
I'll just jump in and say, I know that I presented on one of those papers actually a few months ago. So it has been done and it's done it really well. It's really interesting, the results they've gotten.
What, is there a keyword we could look up?
I just shared the article now. It's called
perfect.
Universal Quantum Controlled Deep Reinforcement Learning. So it controls all the aspects of the computer to, yeah, it's really neat. It's worth a read.
So Jeremy, am I out of a job yet?
No, not quite.
Okay.
Thank you.
All right, heading forward. So these were 3 kind of examples to get you thinking about, I've got an agent interacting with the world, what it needs to do over time can change, and it just is trying to maximize this thing. Oh, and by the way, it doesn't have to be one thing. I could be trying to minimize time and minimize fuel usage. Or I could be trying to maximize my reward in a video game while minimizing time. So you can have multi-objective stuff too. So if you would like to learn about reinforcement learning, here are a bunch of resources, which will also be on the final slide of this talk, which is coming up soon. And most of these are free. I will point out that 3 of these resources are in green, not only because they're awesome, but because they're from U of A. Most of you probably know that U of A, in at least one ranking, is one of the top AI universities in the world. And a large part of that is because of the amazing RL people we have. So that's one of the things that brought me to Edmonton, was those amazing RL people at the U of A and at Amii. Oh, yes, take-home points. You should be thinking about RL. if you're not thinking about RL, you should learn about it and try to figure out if it could be useful, because if it could be a game changer for you. So to summarize, here are some strengths of reinforcement learning. Agent can go off and learn to maximize rewards. Programmer just needs to think about this reward function, not the low-level stuff. Could be a lot less work. Achieving superhuman performance. And you can handle changes in the environment. And unfortunately, it is not perfect. So the agent's going to maximize that reward, whether it is legal, ethical, or what you actually wanted it to do. So for instance, in a game, you might get in a reward loop where you keep doing the same action over and over and getting reward, but never actually solving the level because you didn't think of including that in the reward function. There was the comment a number of years ago that if once the x-axis, the amount of data is exponential, you know it's reinforcement learning. But now, luckily, deep learning has made classified learning slow also. So RL can be very data hungry. If you need something to work quickly, you're going to need to think about how do I make it more data efficient, especially if there is some cost. Now, a lot of solutions are black box, but you can still use some of the techniques that Mohammad was talking about. So if you can summarize a policy in terms of a decision tree, maybe that will be enough to help a user. If you can use something like LIME to say why the agent took one decision instead of another, that could be enough to help a user. One of the things my group is looking at is, can explanations help people trust RL agents more, but also can people use explanations to predict what an agent would do? Because, so for instance, if you can better predict how your self-driving car will work, then you'll be more likely to trust it, you'll be more likely to use it, you'll be more likely to be happy with it. And like I mentioned before, the initial performance could be poor. So you need to think about, if there is this real world cost when I'm starting out, how can I minimize that? So with that, I will say thank you. And here again are resources that you can access. And of course, Warren would be more than happy to point you to the right Amii people if you'd like to learn more. But I am also reachable here. These are the websites I currently appear on. And please, if there's time for questions now, I think, but also if more questions come up later, please feel free to ping me.
Awesome. Thank you so much, Matt Taylor. I think there was a question that came in, just scrolling back through the chat here. Okay, a math PhD student working on RL with math modeling for ICU treatments. Their question is, what are, in your opinion, the best approaches for offline reinforcement learning when you have a fixed data set?
Ooh, okay. So I was saying before how the initial performance can be bad. And one of the ways you can think about this is offline or batch RL. So if I want to learn how to treat a patient, I am not going to let an agent go and explore. What happens if we give this medication? That's not going to fly. But if I had a bunch of information about how patients were treated in the past, maybe I could learn a policy that could mimic the doctor's, or maybe I could learn a policy that could actually outperform them. And this long introduction was me saying this is a really cool problem, and I'm not sure what the state-of-the-art off-policy batch method is, but it is absolutely a current thing that people are looking at. One of the problems is it really depends a lot on the size of the data set and the coverage of the data. Because, so a simple example, if you could cure COVID by giving someone Tylenol and no one ever tried giving a patient Tylenol, there's no way you could learn that. So if the best thing to do has never been seen or hasn't been seen enough, then you'll never be able to learn it without actually taking those possibly dangerous exploratory actions. So that was a long-winded non-answer that batch off policy is very cool, and we've got some experts at U of A. And if I can't remember that person's name, but if you wanted to email me, I'll come up with a better answer and or redirect you. Yeah, Payam.
Sorry if I'm monopolizing the time. Feel free to stop me. I just have a question on a more pragmatic side. I mean, one of the reasons I'm personally, so I work at MDA. I'm a research scientist at MDA. I'm trying to, right now we just got funding to do our first foray into reinforcement learning. I can tell you about it, I guess, hopefully later. But I guess one of the roadblocks that I came across is that, so when you start off in deep learning or any of this stuff, there is so much, it's so much easier to get started, because with RL, there's a lot of choices to be made. There's the platform, there is the environment you're going to work with, there is a whole bunch of libraries. And as an outsider, I can tell you it's not clear which one is, and it seems like even different groups like the DeepMind group, you guys, they're all going in very different directions, and they don't even agree with each other in the papers that you read. So it gets kind of hard to start. So I wanted to get your perspective. If you wanted to approach, let's say, industrial problem, what would you use as a first? And I know you can start with grid world and that sort of thing, but that's usually too simple to be useful. I mean, it's nice to get a sort of intuition about some problems, but I mean, I can tell you what I settled on. So I'm using RL-lib by, I think it's Sergey Levin's group, which, because I like that they say that at least that it's scalable. And I'm trying to build my environment in the OpenAI, based on the OpenAI gym, so customize it based on that. But that's as far as I got, and there's so many choices. So any sort of recommendations of where to start would be helpful.
No, that's right, because you need to think about, am I okay with normal RL, or do I need to use deep RL? Do I need continuous actions or discrete actions? Is this robotics task? Is this a multi-agent task or a single agent? And the frustrating thing is there is no one good answer. And this was absolutely true, even more true 15 years ago. So 15 years ago, I remember talking with people like Rich Sutton about, trying to come up with one good framework. And now the problem is actually we might have too many good frameworks. So I'm not sure that's actually a problem. So I think the decisions you made are absolutely reasonable. But that whole getting started is absolutely a problem. And that's one of the things that by hopefully working with companies, I can better understand how to get this stuff out of labs and into the hands of real companies. Because there's this real activation energy you need to get over that hump. And the more accessible academics like myself can make reinforcement learning, the easier it is to say, okay, come up with a decision tree. If you have this, this, and this properties, you should probably check out TensorFlow. If you have this, this, and this, then you want to go with AI Gym and RL-lib. And and you should definitely use PPO and not DQN. And coming up with those guidelines would be amazing. And another problem is they seem to change every week, because reinforcement learning is hot right now, and there's so many smart people working on it. If you just say, what is the best thing, that's going to just keep changing. So I think coming up with good, these are good things to try, and with hopefully these will remain good things to try for the next year or two, those kinds of recommendations I think could be really useful.
Yeah, please let us know when you come up with that. That would be extremely helpful.
Awesome. So I don't see any other, Warren?
Yeah, I was going to say, this is our last chance for questions, going once and going twice. Okay, well, another round of applause for Matt. Thanks so much. This is great. I personally am very much enjoying this meeting format as opposed to the webinar and, let us talk at you. So it's been really nice to have that interaction tonight. But I'm only one opinion, and we'd really like to hear from you. So you can expect a little follow-up from us in the coming days, where we're going to collect some feedback and be able to get some of your thoughts on tonight's event, and we'll continue to use that as we plan for future events like this. So we're really looking forward to that. I want to say one more quick and heartfelt thank you to our presenters this evening. We really appreciate you taking the time to share your expertise and spend this time together with us on a Thursday night. And we hope to see you again. So you can keep an eye out. Next month is October, and so taking place Edmonton Startup Week, which we are very big supporters of. It's a big activation of our local innovation community. And so keep your eyes peeled. There's going to be a number of opportunities to connect with our team throughout that week, and we have some fun stuff up our sleeves. So we're really excited to connect with you then. And in the meantime, we have really great people, really great programs that we would love to talk to you about. And so you can connect with us at amii.ca. Like I said, new website. Please check it out. It has been a really incredible effort from our team to launch that in the previous weeks. And if you want to send us an email, hit us up at hello@amii.ca. Awesome. And with that, I think we are going to sign off. So thank you everyone for coming out. Again, this was a lot of fun, and we're looking forward to next time.
Thanks, Warren.
Take care.